It's a great pleasure to speak at this conference, and I'm speaking at a short notice, so I had to prepare my talk on my way to France. Well, the talk will be, well, I hope entertaining, but certainly elementary, especially compared to other talks. So I'm actually a representation theorist, not a topologist, but I would like to, describe or to present some nice algebraic structures, very classical, looking very classical, that were discovered actually in the theory of integrable systems in 1990s, and later they were picked up by representation theorists, and it turned out that there is a fairly deep and interesting theory behind these objects. These objects are rings of quasi. Oh, I'm sorry. Yes. Okay. These objects are rings of quasi-invariants. Can you hear me? No? Are you sure that the battery is okay? Okay. I can put it in my mouse. Then I can talk. It's kind of interesting. So classical polynomial invariants of finite reflection groups essentially were born in topology, and they were developed by for topological needs by people like Borel, Serre, maybe I should mention some name, Chevalier, and more recently by Dwyer, Wilkerson. Rodal, maybe I should mention many names. And this object I'm going to describe, it feels like they were supposed to be born also in topology, but in fact, they appeared in a very different field and in some sense very, in some hidden way. Maybe even before defining, I should say that there are a number of counterexamples of different nature related to quasi-invariants. Maybe if you think a little, maybe you can find some counterexamples in topology. These are curious objects. Okay, so let me say a few words first about reflection groups. So I will be working with complex reflection or pseudo-reflection groups. So let me remind you very briefly what these are. So let's take a finite dimensional vector space over a field K and consider a finite group generated by pseudo-reflections So I remind you what this means. So this means that S is pseudo-reflection if it has a finite order, let's say order of S and S, and there exists a hyperplane, which I will be denoting HS, that is pointwise fixed by this automorphism. Well, I will be calling such a finite reflection group Coxeter. So W is Coxeter. If all reflections are real, so this means that they're diagonalizable and have order 2. And there is a very beautiful classification of finite reflection groups, which, well, for different case, maybe I should start with K equals R. So this is the most classical case. So in this case, all reflections are real. And this is very famous work of Coxeter going back to the beginning, essentially, of 20th century. So he classified all Coxeter all real reflection, finite reflection groups. So I remind you that there are 4 infinite families. So A, N, B, N, C, N, D, N, and E to N. So this is dihedral family, and there are 6 exceptions. So E6, E7, E8, F4, H3, and H4. So roughly speaking, these real reflection groups correspond to symmetries of regular polytopes. I should make a remark that not all Coxeter groups are crystallographic. Those which preserve a lattice are called crystallographic, and they correspond to Weil groups. So Coxeter, well, includes but not equal to Weil. Later I will talk about Weil groups. So Weil groups are crystallographic Coxeter groups. So this is over real numbers. Over complex numbers, the situation, the classification is much more complicated. And this is another classical work going back to 50s. Shepard Todd classified all complex reflection groups. So usually, well, they are encapsulated into one infinite family. Which is denoted G, M, and P. So M and P are integers, and P divides M. There are 34 exceptions. Which can be listed explicitly, so you can find in any textbook on invariance theory and classical invariance theory, a table of all exceptional groups. And finally, in later, 20 years later, this classification over complex numbers was refined, or used, probably better way to say, to classify finite reflection groups, pseudo reflection groups over FP and over p-adics. So this is a work of Clark and Even. And later it was even further refined, again, for topological needs by Dwyer, Miller, and Wilkerson. So roughly speaking, for good primes, oh, what happened? That's interesting. Or did I touch it? Huh. Oh, yes, that's. So I'm supposed to keep it like this. Okay, right. so for good primes, in fact, every periodic, every finite reflection group over QP and over FP can be extracted from Shepard-Todd classification. So the precise statement that there is a bijection between conjugacy classes of subgroups over C and over FP and over QP. I will not need a precise statement. I simply want to emphasize that the most important and sort of ambient classification is over complex numbers, and I will work over C for the moment, and later I will refer to these results to pass to finite fields. Okay, so that's all I want to say about reflection groups. And now I can define this main objects. So I will first give definition in the Coxeter case. So let me, definition of quasi-invariants. It is amazingly simple. Nevertheless, as we will soon see, it produces some even algebraic results, which are very hard to prove, which were actually conjectures for quite a while. Okay, so let me take W first, Coxeter. So I will take V to be complexified reflection or geometric representation. Well, one more piece of notation. I will use script A to denote the set of these reflection hyperplanes. Maybe I'll denote them H alpha, and H alpha is shortening for HS alpha. So S alphas are reflections generated by Coxeter group. So let's make the following trivial observation. If I take polynomials, just symmetric algebra of the dual vector space, then a polynomial is invariant. Let me write a trivial statement. Polynomial is invariant if S alpha P equals P for all reflections in W, which is a trivial statement since reflection generate W. Now I will weaken or relax this equation in the following way. So let me fix for each reflecting hyperplane a linear form such that H is kernel of alpha H. And that's sort of first piece of data. And second is most important is let me define on the set of hyperplane what I will call multiplicity function. This is just a function with values in non-negative integers. I will denote it in this way, which is W invariant. So I should say that W acts naturally on A by simply conjugating reflections or mapping reflecting hyperplanes to each other. So I can choose such a multiplicity function. Later I will refine it considerably, but for the moment that's what I need. And I will modify, and this is a definition, I will modify this trivial condition in the following way. So I will say that polynomial P is quasi-invariant, or W quasi-invariant of multiplicity M if instead of equality, I have the following congruence. If S alpha P is equal to congruent to P modulo the ideal, so modulo the principal ideal generated by this linear form to the power 2m alpha. And of course, this is supposed to be for all alpha in A. Yes, so I'm abusing notation. I am simply shortening again notation, just writing instead of H alpha alpha. So this is what quasi-invariance condition is. And I will denote by Q. Unfortunately, Q has nothing to do with rational. It's unfortunately standard notation. So I denote by Q the space of all quasi-invariants for fixed M. So let me maybe call this condition 2. And so this will be the space of all polynomials such that 2 holds for fixed M. You can immediately check that this defines you actually subalgebra, subring inside of polynomials. And let me maybe immediately list some elementary properties which are very easy to prove. Later I will refine and restate them in a fancier way, but let me just state immediately a few elementary properties. So, of course, quasi-invariance. So this is my ream of quasi-invariance, or M quasi-invariance, or W quasi-invariance of multiplicity M. So they obviously contain invariants and contained in all polynomials. In fact, you can show the following that, well, first of all polynomials, if you take m equals 0, this condition is really void, so it doesn't impose any restriction. So these are just quasi-invariants of multiplicity 0, and invariants are, well, quasi-invariants of infinite multiplicity. By which I simply mean intersection of all these rings for all m. So I draw your attention that m is really a function if your root system is not simply laced, or, for example, you can take just decomposable root system, decomposable Coxeter group. So in that case, there are as many multiplicities, as many numbers as orbits of W in the set of this hyperplane. So I really take a hyperplane and assign to every hyperplane integer number, and in such a way that if two hyperplanes are on the same orbit, then the numbers are the same. So, but this is really a collection of numbers. So that's the first property. Now, from this you can, first of all, so what else do I need? Yeah, so QMW, of course, by the way, from the very definition, carries an action of W, so it's a W stable graded subalgebra. And third, well, it is finitely generated module over invariance, and hence it's finitely generated subalgebra. So QM is finite CW module over invariance, and hence finitely generated subalgebra. These are essentially elementary algebraic properties, very easy to prove. So before stating some deeper properties, I will generalize. I should say that this is equivalent, not quite, but equivalent to the original definition, which was invented or discovered, I don't know which word to use, but by geometers, by mathematical physicists, by Veselov and Chalich. think in 90s, 91 too. I do not want to even mention what kind of problems I considered. It's very far. But this definition can be modified, in fact, generalized naturally to all complex reflection groups. So it looks a little more technical, but so let me now extend this definition to all reflection groups. So I take now arbitrary complex reflection group. So in this case, we still have a collection of hyperplanes corresponding to pseudo-reflections. Let me denote them still HS. But unlike in the real case, if I take such H and consider the pointwise stabilizer, which I will denote W sub H, then this pointwise stabilizer will be a cyclic subgroup of order not necessarily 2. It can be of arbitrary order. So this is isomorphic to Z mod NH. And this is the number that I want to introduce. So NH is greater or equal than 2 for all H. So now, in order to define quasi-invariants, I will proceed in the following way. I will consider the group algebra of the stabilizer. And I notice that this group algebra is generated, is spanned by idempotence, which I will denote. Let me make it, which I denote EHI. So this is a basis of idempotence, which looks as follows. I take a determinant character to power I. I runs from 0 to NH minus 1, over W times W, and I runs from 0, 1 to NH minus 1. Right? So I define such idempotence, and then I notice again that a polynomial is invariant if and only if all this idempotence except for I equal 0 kill polynomial. So if EHI equals 0 for all I 1 dot 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 NH minus Y. So now after this observation, if you look at the Coxeter case, you can think a little and you will see how you can modify this condition. So for this, I have to, again, fix alpha H, a linear form for every H. And, and I also have to fix now NH minus 1 integers, which I will simply denote like this. So this MHI are a collection of non-negative integers. For each hyperplane, I have now NH minus 1. So I 1 dot dot. It will be convenient for me to start numbering this from 0, but I will always assume that NH0 is 0. So really we have NH minus 1 multiplicities. And again, I will assume that these multiplicities are invariant under W in the following way, that if I have two hyperplanes, H and H prime, which are on the same orbit, then multiplicities with the same I are the same. I equal if H prime and H are on the same orbit. And what I can do now, I can simply use these multiplicities to modify this condition, and this is the definition that first appeared in my paper with Elliptical. Yeah, I should have mentioned that this Coxeter case was studied by means of representation theory by something which is called double affine Hecke algebras, and using quasi-invariants, several interesting conjectures were proven, and it was not so easy to actually generalize. That was, I should say that something about references. So this is in the work of, in my work with Eitenhoff, Ginzburg, and Ginzburg. So most results I'm going to mention in a moment are proved in Coxeter case in that paper. But in Coxeter, in complex case, well, in fact, in that paper there were several mistakes, very subtle actually, very subtle mistakes. And only looking at complex quasi-invariants, these mistakes were detected. But anyway, so the definition is the following. So P is a quasi-invariant of multiplicity M if the following congruences hold. Let me put them here. Now I simply put NH times MH I here. And again, they should hold for all H and for all I, starting from 1. So that's, again, if you look at this lemma and assume that W is a complex reflection group, you can see that almost all statements hold, except for arbitrary M, for arbitrary multiplicities, this subspace QMW is just a subspace. It's a module over invariance, but not necessarily a subring. So is a space of quasi-invariants of fixed M, multiplicity M. So this lemma 1 holds, except QM is not an algebra in general. And so let me now state the first, well, non-trivial algebraic theorem about quasi-invariance. I should say that there are several proofs of this result, and sort of despite its modest appearance, it's still non-trivial theorem. You probably can guess what the theorem is. For M equals 0, it's a classical result. Unfortunately, the proof doesn't work in general. So, so theorem 1, so this was proven first in my paper with Eitenhoff and Ginzburg. In Coxeter case, and with Charlie in complex case. So the statement is very simple. So QMW for all M, for all multiplicity, QMW is actually a free module over invariance of rank equal the order of the group. Right, so if M equals 0, this is just the polynomial ring, and this result is the theorem of Serre-Chevalier. So M equals 0, of course, is well known. But for arbitrary M, strictly speaking, the proof is not quite algebraic. It uses representation theory, which uses some results on, on monodromy of some knižnik-zamolodchikov connection, which is some computations in analytic differential equation. So one of the motivation for me to kind of do what I do, namely to try to resync this topologically, is to find a more natural proof of this statement. Okay, so right. Okay, now let me. In fact, this theorem was maybe since to finish this overview. So this theorem is actually a consequence of another deeper theorem about d-modules on varieties of quasi-invariants. So I will leave some space, and later I will state it. So, our ultimate goal is to try to find spectral refinement, actually, of these results. Surprisingly, that for theorem 1, there is a very natural one. For theorem 2, still not, but I will mention. Okay, so last thing I want to mention before going to topology is the following, that there are several generalizations of quasi-invariants, and perhaps most relevant for us so-called multiplicative and elliptic generalization. I will not state precisely definition. I will simply mention this. Generalizations. So there is a multiplicative generalization, so-called multiplicative quasi-invariants. Multiplicative, which are defined in a, of course, for, now I have to assume that W is a Weyl group, that there is a lattice associated to it. So this is a certain sub-ring inside of the group ring of the weight lattice of a root system of W. And there is also very nice elliptic version, which I will denote QM elliptic. And elliptic quasi-invariants of, let's try, elliptic quasi-invariants. There is what? If you lift this one, oh, I see. Well, I am left-handed. I can use right hand for something, right? So, so they actually live. So they actually live in the space of graded global sections of abelian variety that is associated. Well, so I have to fix elliptic curve. For people familiar with elliptical homology, probably this will ring the bell. So you take a co-root lattice, that's what Q-check means, tensate with fixed elliptic curve. You can take a Tate elliptic curve, for example. There is a classical work of Luyenga who showed that on this abelian variety there is a distinguished line bundle called, nowadays called Luyenga bundle. And so what I'm doing, I will simply take graded global section of this Luyenga bundle. Well, it depends how you define it. Quasi-invariance, elliptic quasi-invariance is certain distinguished subring inside of this cohomology group. There are several actually versions I don't want to specify at the moment. There are several definitions of quasi-invariance, but it seems that now we know probably the correct one, the one which comes from topology, the elliptic homology of spaces of quasi-invariance, but I will simply mention. Okay, so now let me, so what I'm going to do, I'm going to realize these algebras of quasi-invariance topologically. If you, of course, try to do it naively, the question is trivial, thanks to Quillen. So rational homotopy theory tells you that, well, every reduced locally finite graded algebra can be realized as rational over field of characteristic 0 can be realized as cohomology ring of some simply connected space. That's not what I'm going to do. Instead, I will try to look at this algebra of quasi-invariance, create varieties associated to it, and formalize or axiomatize geometric properties of these varieties. And then I am going to state homotopy theoretic versions of those properties, and realization problems that I'm going to look at is a kind of, more sophisticated in the sense that I'm going to ask not for a space for a fixed M, but for a diagram of spaces for all M, and with extra additional properties. So let me, okay, so that's the idea. Any questions? Probably I'm going too slow, but I will cheat in the end. I have my slides prepared. If I am going too slow, I can switch to slides. But I am going to state precisely what, precisely these axioms, and then in the end I will state the theorem. And depending how much time I have, I will explain what we know at the moment. Unfortunately, we do not have the proof of this, well, not the proof, not quite satisfactory solution, but in many cases we do have. Okay, so so let me first define geometrically varieties of quasi-invariants. So first I have to deal with the question that when we work with complex reflection group, quasi-invariants do not form a ring. And it turns out that it's not difficult to exactly find a restriction of combinatorial nature on multiplicities that give us sufficient and necessary condition for quasi-invariants being a ring. So let me make it as a lemma. So W is a complex reflection group. And now here is an observation that QMW is a subring if and only if multiplicities satisfy the following conditions. the following inequalities. Let me write them. This is a kind of purely combinatorial statement, but you can easily check. So if less than nh and well, there are several ways to write, but let me write this way. So if I plus k greater than nh, so of course for all h. Okay, so if n equals, so if w is Coxeter, so this system of inequalities is void because nh equals 2. So in this case, Qm is a ring for all m, always a ring, which you can check directly. But if W is complex, for example, simplest case, well, if you take, for example, cyclic group, Z mod 3, which is a complex reflection group of rank 1. So in this case, for example, you can easily see that, well, there are two multiplicities, and they satisfy two inequalities. Well, it will be clear in a moment why I am, oh, I forgot to, okay, let me just move it up. So what I will do now, I will restrict to multiplicities satisfying this condition. I will take the set of all these multiplicities and put a natural partial order, making it a passet. And then I will think of my, for each point in this passet, quasi-invariants form a ring. So I can consider the corresponding affine scheme. And in this way, I will get a diagram of schemes parameterized by over this passet of multiplicities. And I will try to summarize in geometric terms what this scheme, properties of this scheme. So that's the idea. It turns out that well, these passets are quite non-trivial. Well, at least let me maybe show you a picture. In the simplest case, I have to get down my blackboards. Yeah, it's so these are actually, I would be very interested to see if you recognize some of this. So these are just the first two trivial cases, Z mod 3 and Z mod 4. These are passets of algebraic multiplicities. So let me define what this M formally ML mean. And then list properties, and then I will simply one by one write homotopy theoretic analogs of these properties and get some nice axiomatics. So, right. So this is definition. So M alg W. So these are all multiplicities. Let me simply say subset of multiplicities M. So satisfying, satisfying the inequalities that I think which I erased, satisfying the inequalities star. So with the following partial order, so if I have two collections, so I simply call one is greater than the other. So for all so you can easily, for Z mod 3 and for Z mod 4, well, calculate what exactly these multiplicities are, and you can draw this passet. So if you go to higher ends, the passets getting more and more complicated, even in rank 1, even for Z mod n. For other reflection groups, they're quite complicated. Okay, so now I can state my properties and switch to topology. Okay, or maybe maybe I shorten a little bit, and or maybe I will show you slides with topological axiomatics, carefully stated. So I will define VMW as spec QMW for all M in this passet of algebraic multiplicities. And then, so in this way, so notice that QMs themselves naturally define me a diagram of commutative algebras of shape, well, of shape of the opposite passet. And by taking spec, I will get a diagram of affine schemes of shape M alg. Well, I work over C. I will simply visualize this diagram as a tau. So Fm equals 0. This is just my vector space. And then I have, well, then I have to every element of this passet attach an affine scheme, and to every partial order I can to every order I can attach a map. So let me denote this map somehow. So P M prime. So this is how I visualize this functor over this passet of algebraic multiplicities. And now let me state the properties. So first of all, this is a diagram over, so every space of quasi-invariants, every scheme comes with a map to algebra geometric quotient, or maybe better to write it this way. So they really form a diagram over spec of invariants. And all maps are W equivariant, so all VM are W schemes, and all maps, all morphisms are W equivariant. And I will denote this maps by Pm and Pm prime. So this is the first property. So this is a diagram of W schemes over this algebra geometric quotient. So second, let me call this diagram star. So this star converges to invariance in the sense that if I take a column over this diagram, over this facet, then this map induces me isomorphism. These are just formal properties which you can easily prove by passing to algebras. So the third property is that, let me state it a bit formally. So each map Pm factors through the projection into W, and the induced maps are all isomorphisms. So this is just a fancy way to say that invariants inside of quasi-invariants are all invariants. So for all n. So these are formal properties, but there is one which is much less obvious, and in some sense most crucial, is the following, that all these maps Pm, all these morphisms of schemes, Pm m prime, are so-called cuspidal quotients. Which means, so these are finite dominant maps of schemes which are set theoretically injective on close points. So if we work over complex numbers, so these maps are bijections, but not scheme theoretic isomorphism. So scheme theoretically injective on close points. So maybe this is not very standard terminology. This property, now I promise to state something last theorem 2, but I can state it as follows. So this property, theorem 1 plus property P star, implies, well, one of these counterexamples I mentioned, namely, so these schemes, or these varieties Vm are actually algebraic varieties, which are, of course, singular, but nevertheless, you can naturally define differential operators on such varieties using, there is a Grothendieck construction of differential operators, not topological Grothendieck construction, but so you can define naturally the category of D modules even if these varieties are singular, and it turns out that this category is actually equivalent to the category of D modules on just affine space. So these maps with respect to D modules behave essentially as isomorphism or equivalences. Oops, okay. That tells me that I have 5 minutes. Okay, so now let me maybe, to save time, switch to my slides and give you topological reformulation of these axioms. Oops. So I should use this one. Okay. So maybe these are slides prepared for a different audience, so this theorem probably doesn't need introduction. So I fix now a compact connected Lie group, a maximal torus T in G, and consider this canonical vibration from BT to oh, sorry. Oh, I should have practiced with this. From BT to BG, and this, the classical result of Borel tells me that this map induces injective algebra homomorphism, and its image is precisely W invariance, and moreover, in fact, W invariance in reflection representation, where V is second homology of BT. So this is kind of, if you wish, for me, it's a way of realizing classical invariance. So I want to generalize this theorem in such a way that I will get realization of quasi-invariance for V8 groups. So what exactly the properties are that I want to satisfy are the following. So I take G and T as in this Borel theorem. So G is compact-connected group, T a maximal torus. Now what I would like to construct, I would like to construct a diagram of spaces over this poset MW. Since W is a VL group, there is no need to restrict to algebraic multiplicities. So I'm simply omitting this index algebraic. So I would like to have a tau of spaces together with maps Pm from Xn to Bg, one for each m, satisfying the following 5 properties. So, and you should compare these properties with the ones I mentioned in case of schemes. So first of all, every Xm is a WCW compass, W space. All maps are equivariant. P0 is just Borel vibration. Well, of course, so in other words, to summarize, I can simply say that this is a diagram of W spaces over Bg. Then this property that my affine schemes converge to algebra geometric quotient, homotopy theoretic analog is the following, that homotopy colimit over this poset of this diagram, the maps Pm that are part of the construction induce weak equivalence to Bg. So the spaces give homotopy decomposition of Bg. Well, third property is that, this property is a homotopy theoretic analog of invariance, is the following, that this maps Pm factor through the inclusion of Xm into the space of homotopy orbits, W homotopy orbits, and the induced map is cohomology isomorphism. So there is a commutative diagram, so Xm maps to Xm HW, and the induced map induces isomorphism on cohomology groups. So these are first 3 properties, and the second 2 are really, the last 2 are really tell me that these spaces realize quasi-invariance. So each map Pm induces an injective homomorphism on rational cohomology, and with this natural identification, cohomology of Bt is a polynomial real over Q. This maps pi 0 m induce isomorphism with Qm, the subalgebras of quasi-invariance. So these are the 5 properties that I want to satisfy. Well, the main theorem is the following. So this is work in progress with RJ Ramados, is the following, that for any compact connected Lie group, they exist diagram of spaces satisfying all these 5 properties, with exception, well, that property 4 and 5 hold for even dimensional cohomology. So there are in fact 3 different constructions, and each actually produces spaces which do have odd cohomology. The reason being that we construct such spaces using gluing using homotopic limits, and the problem is, of course, the problem of higher limits. So it is, in this sense, it's not quite satisfactory, but so it's still not clear whether they exist really in general. But for certain groups, there are constructions that actually give exactly realization without really odd cohomology. So what is interesting is that this spaces Xm, if you take a homotopy fiber of this map Pm, so we call this spaces Fm, and these spaces actually G spaces, and Xm appear as homotopy quotients of G action. So we call these spaces FMGT quasi-flag varieties. Well, they're not varieties, just homotopy types, but and they can be also axiomatized in a similar manner as a diagram over this MW. Now I can very quickly explain these formulas on the board by simply saying that if you take the spaces Fm and compute G-equivariant case theory, you recover exactly multiplicative quasi-invariants. And you can, if you compute elliptical homology, you recover one version of elliptic quasi-invariants. So, so this computation have been done not in general, but in certain cases. Maybe, can you give me 1 minute? I will give you a proof of this theorem in one line for SU2 to convince you. It's kind of amazing fact. So for SU2, for GSU2, all axioms, all properties that I have stated follow by very well-known probably to topologists construction, which is called Ganea construction. So this Ganea construction is called fiber-cofiber construction. It is actually formal. It can be performed in arbitrary model category, infinity category if it's pointed. In fact, you can perform it in the category of derived-affine schemes, for example. In that case, you recover the spaces of varieties of quasi-invariants. So what is this construction? You start with a fibration, X to B. You take homotopy fiber and then take homotopy cofiber of the inclusion of homotopy fiber. And you keep going. So the result is a tower of fibrations, starting with original fibration, homotopy fibration sequence fxb, and you produce a tower of spaces. So for SU2, if you start with the classical barrel fibration, this produces you a tower of spaces which precisely satisfies the axioms that I listed. So as you can see, this property P star, well, the property cuspidal quotient property is kind of realized by these fiber-cofiber maps, so-called Visca maps. So the problem, if you think a little, and even in rank 1, maybe I'll show you last slide since I can do this clicking. For complex reflection group, in the simplest case for Z mod n, you can write down a similar axiomatics for P local groups. And if you, instead of Borel fibration, you start with a Sullivan fibration for Sullivan spheres, you can actually produce the entire diagram by certain generalization of this Ganea construction. We call it Ganea diagram of a shape of a passet. To this passet, you can define abstractly what Ganea diagram is. And then the main theorem that's carefully proven that for Sullivan spheres, complex quasi-invariants for Z mod n can be realized in terms of P local spaces. So I'm brief, but for experts should be clear what I mean. So there are a lot of technicalities here. So first of all, you have to work with cohomology groups, not with coefficients in QP, but with coefficients ZP with Q. That's creates some problem, but yeah. So in rank 1, the situation is very clean, and in higher ranks, there are partial results. So in particular, this question of odd cohomology is still quite open. Okay, thank you very much.
Back to examples.
Yes.
Like the group GLN and the values symmetry group. So you have this approximation.
Oh yes, for symmetric groups, quasi. Yes, well, maybe I should. Let's see if I have references. Okay. So yeah, I have very few references. Yes. So for symmetric group, quasi-invariants have been studied heavily by combinatorialists, but not with much success. So for example, the theorem that I mentioned, which looks like should be proven by combinatorial means, is still not proven. So there is a sequence of papers, in fact, a book by Andriana Garcia and Wallach, for example, who specifically try combinatorially prove this Cohen-Macaulay property for varieties of quasi-invariants in terms of, by combinatorial terms. So one little, so what you can do with spaces, right? So you have the spaces XM, you can define Kachane spectrum of such a space, and then, well, at least in rank 1, we checked that this Kachane spectrum has topological Horenstein property, which sort of refines this algebraic theorem, not in general, but just for, and using the work of Dwyer, Iyengar, and Greenlees. So they form this Kachane spectrum of this. Yeah, I should say something related to stable homotopy theory. So you can, for the spaces XM, you can define this Kachane spectrum. And then for any field K, so this is Gorenstein. Well, to be precise, it comes with augmentation map. So this morphism is Gorenstein commutative ring spectrum of shift. Yes, I'm not. Rank G minus 4 sum of multiplicities. Well, so experts know that in this spectral world, Horenstein property splits, so it's also satisfy Horenstein duality, so with the same shift. And this is expectation in general. It's proven in several cases, but there is no uniform proof so far. So the real question is, what is a spectral analog of this differential equivalence theorem? And I was going around and asking experts if anyone defines things like differential operators on commutative ring spectra. Maybe it's my question to the audience. Well, I have a candidate, but...
So you're asking the question.
Yes, now I'm asking the question. That's why I came here. Okay.